Thanks, Anthony. Thanks everyone for coming to our seminar this month. We're really excited to hear Lucas and James talk about their work on the solar atmosphere. I just had a few quick announcements I wanted to highlight before jumping in. We are soliciting some information about setting up a newsletter and what to include in that. We've sent that out to our mailing list, where we're looking to include things on announcements on upcoming workshops, job postings, relevant paper publications, and so forth. So we would encourage you all to fill out that form. We've sent it to our mailing list. If you're not on the mailing list, please sign up. We will be sending these newsletters out to that. And if you'd like us to send you a link to that Google form, contact us and we'll make sure to do that. We are also looking to set up a workshop in the near future at Johns Hopkins APL. It's most likely going to be hybrid, but we are also soliciting your preference in that Google form, whether you'd like to be in person or virtual. And also, we strongly encourage you to fill out, we have our potential dates for that workshop that we could hold it. So we strongly encourage you to fill out your preferences so that we can select the best time possible going forward. And also, I think there's a strong desire to include announcements in this newsletter. So if you do have announcements you'd like us to send out as part, please send us an email and we'll include that in the next installment. Additionally, we are soliciting speaker suggestions. So if you would like to present your work or know of someone that you think would benefit from presenting here to this audience, reach out and we will make sure to include them on our schedule going forward. And as always, all of these presentations are recorded and we will make them available on our YouTube channel, which you can come back and view anytime. So I will pass it off to Anthony now, who will introduce our speakers.
I'm not getting any audio.
Yeah, okay, I'm not sure. Anthony, we can't hear you. I wasn't sure if that was just me.
Hey,
thanks,
does
Lucas.
that work?
Yes, now we can hear you.
Okay, cool. All right, so everyone's read the slides on here, read what's on the slide here. If you have any clarification questions during the talk, feel free to enter them in the chat or raise your hand. Otherwise, we'll save all the discussion questions for the end. So with that, to introduce our speakers today, we'll be hearing from Lucas Tarr, who is an assistant astronomer at the National Solar Observatory, and James Leake, who is a research astrophysicist at NASA Goddard. And both their backgrounds are in solar atmosphere modeling, so naturally we'll be hearing about their work on developing data-driven hydrodynamic models of low solar atmosphere. So please go ahead. I think James will start us off.
Yeah. So can you hear me and see the slides okay?
Looks good.
Yes.
Yeah, great. So yeah, thanks for having us. This is work that we've been doing a group at Goddard, myself and Peter Shook, Lucas and Dylan Key at NSO, and Mark Linton at the Naval Research Laboratory. So Lucas has kindly let me give some introductory slides, even though he's the one who's done the majority of the work on this recently. But I thought I'd set the scene for the solar modeling that we do. So our motivation is obviously understanding the coronal magnetic field, because it's vital if you want to answer the main questions of solar physics. So if you're interested in the solar wind, and you're seeing on the right there, that's an image from an eclipse where you're seeing the coronal plasma emission. And that structure is determined by the structure of the magnetic fields. And the solar wind is different whether it originates in regions of open or closed magnetic field. If you're interested in the problem of the coronal heating, so the solar corona, the outer atmosphere, is 1,000 times hotter than the observed surface. The proposed mechanisms for that are magnetic reconnection and waves in the magnetically dominated plasma. So by magnetically dominated, I mean that the plasma pressure is much lower than the magnetic pressure. Other areas of interest are obviously solar activity and the eruptive events that we observe on the sun. So basically, the solar dynamo is generating magnetic fields. Whether you think that's deep in the convection zone in the tachocline, or if it's some kind of surface dynamo, but what happens is those fields emerge through the observed surface, and we call those active regions, the sunspots that we see. And these active regions exhibit eruptive events where mass and plasma and particles are ejected towards the Earth sometimes. And we believe the energy is stored and released in the magnetic field in the corona. And so we want to know the background field and the ejected field if we're to determine if these events are going to be geoeffective. So unfortunately, we only have inferences of the magnetic field based on the plasma emission. There are new observing programs like the Daniel K. Inouye Solar Telescope, which Lucas works on at NSO, which people are working on how to infer the field in the corona using that, also using ALMA, the large millimeter and submillimeter array. But currently, the best inferences of the magnetic field are at the optically thick photosphere. So basically, the Solar Dynamics Observatory has an instrument called HMI, the Helioseismic Magnetic Imager. Lucas will go into a bit more detail on that. But basically, you can invert, using certain models, you can invert the plasma emission to get what you think the magnetic field is at the photosphere. And currently, we're able to obtain full sun vector magnetograms on a cadence of somewhere between 1 and 12 minutes. And the bottom left image there is a composite image, and what it's showing, the color, the orange and blue, is showing a sunspot pair. So you're seeing positive and negative normal magnetic field on the photosphere. And overlaid on that is some ultraviolet emission showing the kind of structure of the plasma, what we call these coronal loops. And it's the magnetic field that determines that structure. So this is the kind of thing that we're interested in modeling. So if one of the things I'm interested in particularly is the onset of solar eruptions, whether sometimes these are called coronal mass ejections or prominence eruptions. There's a terminology that's used. They're usually associated with solar flares, where energetic particles are accelerated and sometimes impact with the Earth. So the prevailing theory is that the energy is stored and released in the coronal magnetic field, in the current of those magnetic fields. So if you think kind of twisted and helical structures in the corona, these are the sources of these coronal mass ejections. And the reconnection of the magnetic field is key to releasing the energy that's stored. So the energy is built up slowly over days and weeks, and then is released very quickly in minutes to hours. So this non-potentiality, we believe, is kind of brought into the corona in two different ways. You could have complex structures emerging from the convection zone where they're generated by the dynamo action. They emerge through the photosphere into the corona and then erupt. But also the surface motions, because the photosphere is high density and the corona is low density, the plasma motions can kind of twist up and energize the magnetic fields there. And then that energy is released through magnetic reconnection as a CME. So these flows are, we have convective flows on small scales. We have sunspot rotations, differential rotation, shearing flows. All these can energize the field. So one of the main questions we want to ask is how and can we predict when this energy that's built up is released? Because that would be great for predicting whether a CME is going to occur. So I work in these kind of idealized models where we kind of take simple structures. The basic building block of coronal magnetic field is a twisted flux rope that's got some free energy and that's going to power this eruption. And basically we have an idealized solar model. There's a little patch on the sphere of the sun, and you start with some idealized initial condition, and then you mimic the photospheric evolution. So here you see, this is some work I've been doing with, Tibor Torek at PSI has been doing this using some of our simulations. You mimic the emergence of a new active region, which can destabilize an existing one. And then through magnetic reconnection, it allows this basic building block, this flux rope, to erupt. So what we want to do is replace this kind of idealized model with a model that uses the data that we have. We have full sun vector magnetograms on a cadence sufficient to infer what's going on at the boundary of our simulation. So just a quick review of the type of model, the equations we're using. Even though the corona is collisionless, because we have such large scales, we can get away with a fluid approximation. You take moments of the kinetic equation to give you your conservation of mass, momentum, and energy. You combine that with Maxwell's equations for the electric magnetic field and a closure using generalized Ohm's law. Typically, a lot of models are ideal, so there's no collisions, no resistivity in that model, apart from on very small scales. And that's a problem in coronal physics. You have large scales that are driving the system, and it's the small scales that the dissipation occurs. So at a bare minimum, because we're in a low beta environment in the corona, at a bare minimum, you want to know what the magnetic field and the velocities are doing. And a natural lower boundary is the photosphere, because that's where we have the best inferences of the magnetic field. And Lucas will go into more detail about that. And also because it's high density compared to the corona, the plasma motions are driving the magnetic field above. So it's a natural boundary to input some observations. And in addition to the magnetic field, you can use methods to infer the velocities as well, based on the equations of motion. The problem is this lower boundary, which we're hoping to, assimilate data into, is also open. It's the boundary where all the mass, all the flux, all the energy comes through. So naively, the question I asked, and I don't know if it's a good question to ask, is how do you do data assimilation on an open boundary? We're not doing data assimilation inside the simulation domain. We're doing it on a boundary where all the important stuff is coming through. So historically, there's been different ways to incorporate the observations into the models. And I would say that data assimilation is very much in its infancy for coronal modeling, at least with regards to the photosphere. So the kind of one of the simpler things you can do is just do a time series of extrapolations. So you take your photospheric boundary where the magnetic field is, and you do a volume filling extrapolation under some assumption, like there's no currents, J equals 0, or the Lorentz force is 0. That's called a force-free extrapolation. And the top right image there, you see, the normal magnetic field in the gray scale superimposed with some field lines from that extrapolation. And then you could maybe do a visual comparison with the plasma emission. So this is from the SDO. This is ultraviolet emission, showing you the coronal loops, the heating of those loops. So you could do some kind of visual comparison to see how good it is, and then just do a time series of extrapolations to see what's going on as the photospheric field evolves. You could also do something completely different. You could do a data-inspired model, like I mentioned earlier, where your initial condition or your boundary conditions reflect what you're seeing in the observations. This approach is good if you really want to focus on a particular mechanism like reconnection, or some theoretical model you have, like an ideal instability, like a torus instability that drives the eruption. But obviously you're not using the data as best you can. So the way we want to go is what we call data driving, which is basically you periodically update the lower boundary with the magnetic fields on the cadence that we can get them, the best cadence we can get them. And if you reduce the physics of the problem, if you don't use the full magnetohydrodynamics, you can run this relatively quickly. And that means it's good. It has the potential for running in real time and being able to predict future evolution. And there's a nice review by Toriumi a few years ago, where they did this kind of shootout of a couple of different data-driven models. And it kind of like was similar to what we did in the paper a few years earlier, where forget the observations, let's take a dynamic simulation where we actually model the magnetic field emerging from the convection zone into the corona. And let's pretend that's our real observation, and we have all perfect information of the system. Now let's extract a fake photosphere, and that's on some kind of cadence similar to the observations. And then we can give that data to a new model that just ingests that information at the lower boundary, and then evolves above, and you can compare your data-driven simulation to your ground truth to see how well that approach is done. And Toriumi did this on a few different data-driven models. The issue, I think, I mean, the results were kind of fair to middling. The issue was the majority of those models, I think nearly all of them, if not all of them, reduced the physics to be able to run. Basically, they ran a magneto-frictional model where you basically ignore the plasma and you set the velocity to be proportional to the Lorentz force. Or you just assume that your atmospheric domain is just the corona. There's no high density region down towards the surface, because the density increases 8 orders of magnitude as you go from the corona to the surface. So forget those lower stratified region of the chromosphere, the transition region, and just put your data in the corona. The problem with that is you're using magnetic field data from a region of high density, high plasma beta, and putting it in your lower boundary in the 0 or low beta model. It's just not consistent. And that, I think, is the source of the reason that a lot of these shootout results are not great. So we propose that you need to run the full MHD equations and ingest the data at the photospheric boundary. That's a problem because if you consider the full MHD equations, you then have to make sure that the data you're putting in is not only consistent with observations, but consistent with the system of equations that you're running. And Lucas will go into that in a lot more detail. And he's going to talk about the method of characteristics, where you recast the MHD equations in the characteristic form. So think the evolution of disturbances, like think waves. And then at the boundary, you can determine whether you are allowed to choose the incoming or outgoing characteristics based on what the system is doing. And when you're allowed to do that, you can then try and fix those characteristics such that your boundary is consistent with the observations and the system of equations. And as far as we can tell, this has not been implemented yet in full MHD, and for good reason. Lucas has been working on this in detail for a while. So I guess I'll hand over there to Lucas, and he can go into more of the details. Thanks.
All right, thanks, James. Okay, so yeah, I think James well summarized kind of what we're trying to do here and why we're trying to do it the way we're trying to do it. So I'll just jump right in. I'm going to spend a little bit more time talking about this lower boundary, because I think that's a big point of difference between what we're doing in solar physics and what sort of other data assimilation methods are doing. Then I'll go into some of the details about how we're trying to set up this data-driven method, and then talk about some useful cases for doing this with a Sphera Mac, and then kind of take a little bit of a side jaunt at the end to talk about how to set up a very, very general non-reflecting boundary condition that's sort of inspired by how we started thinking about trying to do data driving. So just first off, I'm going to do even a little bit more background on the sun. What does it look like? Here's an example from a few days ago from the Solar Dynamics Observatory. This is showing continuum emission. So if you got on a pair of very dark glasses and went outside and looked at the sun, this is what you would see. You see sort of this disk with some modeled features, and you see the sunspots. The sunspots are regions of strong magnetic field, and we can actually, as James showed earlier, we can measure what those magnetic fields are on the sun using properties of spectral lines. And this is what the magnetic field, a map of the magnetic field looks like at that same time. So blue regions, I think, are out of the sun, red regions in this are into the sun. So you have these sort of loops popping in and out of the sun, and they line right over the magnetic field. That's because the magnetic field is very, very strong and intense, strong enough to disrupt the convection pattern on the solar surface. If you look higher up, you can see this sort of hot ultraviolet emission from these field lines, and that gives you an idea about what the structure looks like up in the corona. So this is about 750, 800,000 degrees is where this iron line, the emission in this iron line that we're looking at forms. It also gives you an idea about how far off the surface of the sun and how high up into the atmosphere the magnetic field structures the plasma. So this is where we really get all of our information. And I think an important thing to point out just once more is that we don't get any information, what we would call in situ. We can't fly spacecraft this close to the sun. Parker Solar Probe is getting close, but it's not getting this close. So we really don't have any direct confirmation or direct ability to measure the properties through the solar surface, which makes data assimilation very difficult. Whereas we do have good remote sensing possibilities down at the solar surface. So here I'm showing an example of that really remote sensing at that lower boundary at the photosphere is the name of the game. So this is showing a sunspot magnetic field. Around it, you can see the granulation pattern. This is from continuum emission right at the surface of the sun. So this is the very top of the convection zone. And this is data from the Hinode satellite, which has a spectrograph. And so if you take a slit along this direction, you throw the light from that slit onto a diffraction grating, and you disperse the light in wavelength, then you see, let me switch to a pointer here. Then you disperse the light in this direction, and we see the wavelengths. And here you can see a couple of dark spectral absorption lines. These happen to be the iron 1 lines that are formed down the photosphere. The red line here shows, we plot the spectra along this red line here, and that's shown down below the iron 1, 6301 and 6302 lines. And that's from this dot right here is the specific location. And we can also measure, if we have a polarizer in front of our detector, then we can measure the linear and circular polarization. And that fully describes the Stokes vector. And now we have a good description of what the spectral line looks like and what all its properties are. The polarized light, of course, comes from, in this case, the presence of magnetic field. So you already have a sense that from remote sensing, we can get an idea of what the magnetic field looks like on the sun, whether it's circularly polarized or linearly polarized has to do with the orientation of the magnetic field. The amount of Zeeman splitting from the separation of the energy levels in the atomic spectra has to do with the strength of the magnetic field. And then, of course, we can use the properties of the spectral lines themselves to get Doppler velocities or to get temperature and density measures. And that all comes from low down on the photosphere. So how do we actually determine the details of that lower boundary? Typically, you start with some sort of model atmosphere, where if this is sort of the surface of the sun and this is moving out into the solar atmosphere, the density falls off, the temperature increases, and the magnetic field has some sort of shape. I'm not going to go into too much detail here. There's an entire cottage industry figuring out how to do this, but you do your radiative transfer equations through this 1D system or maybe through a 3D system if you use 3D effects, and you get your observed spectra out. On the other hand, if you have an observed spectra, you can solve the inverse problem and figure out what sort of model atmosphere really generated the light that we see and we observed through this remote sensing techniques. And again, I won't talk about that inversion problem, but it's really fundamental to getting all the data that we're going to use for data driving. So then the real question is, okay, we have all these spectral lines on the sun, where do they form? And again, we turn to models for that. This is showing an example here of continuum intensity as sort of this grayscale model pattern on the bottom, and a volume rendering of the temperature as these large loops here. You kind of can pick out two things right away. The continuum intensity forms at a very compressed height, low down in this atmospheric simulation, whereas the temperature, this is showing temperature at 10,000 Kelvin, has a lot of structure throughout the 3D volume. And the reason for that is really because the density drops off very strongly with height. So this is density on a log scale. The surface is at 0. This is the convection zone with sort of an adiabatic, nearly adiabatic density. And then a steep drop off as the temperature really increases, the pressure scale height increases, and then the density flattens out up in the atmosphere. So you perform your radiative transfer through this type of a model, and you ask where do different spectral lines forms, and you get sort of this plot here. This is showing the solar surface along this axis, the solar height along this axis. This is basically a cut through this simulation, through I think the middle of the simulation. And you see where these different solar lines form. There's a magnesium 2 line. It forms in this purple kind of wobbly line here. You can see it's all over the place in height. Same with the calcium line in blue, the hydrogen alpha line in orange. The calcium line forms over a very broad range of heights. That's in red. But as you move down towards this high density photosphere, you get something that looks like the iron 1 line that I showed earlier. And that's this green band right here. And there's a couple things to note about it. One is it's relatively flat. So the granulation scale here, one of these granules is about 2 megameters across or so, and it's pretty flat over those levels, unlike these other lines higher up in the atmosphere, which are shifting around and where they form. It also forms over a relatively narrow range of heights. And those are the things that really make the photosphere a very good surface at which you can just take it and shove into a simulation as a lower boundary. And that's why we're trying to do it this way. So that really leads to the situation where the photosphere is a true physical boundary, again, because of this density, high density stratification, and because the field is anchored down in that photosphere. We also have the fact that we have these high cadence observations. So we really have a good understanding of how that lower boundary is evolving in time. So this is showing the emergence of an active region. White things here are a magnetic field along the line of sight pointing out of the sun. The black regions are magnetic field pointing into the sun. And you see this sort of evolution of the field over several days. And if we look at kind of the timescales involved here, the typical photospheric velocities, if you track a little feature on the sun or you look at the Doppler velocities from the granulation pattern, you get something like a kilometer per second. Whereas the sort of distance across this sort of active region, the strong magnetic field region, is about 150 megameters, which tells you that your photospheric sort of evolution time scale, your crossing time of this feature through the photosphere, is about 40 hours, which is roughly amount of time it takes for one of these regions to emerge. This happens over 4 days, so a factor of 2 there, but it's about the same. But if you think about what the time scales up in the corona are like, so this is showing another one of those ultraviolet emission lines that shows these nice coronal loops. This is the same sort of field of view here connecting these regions. You ask what the travel time along one of these loops is. That velocity is set by the Alfvén speed up of the corona, with typical values of the coronal magnetic field and densities. You get about a megameter per second, whereas your length scale is maybe 100, 200 megameters. And that means your crossing time up the corona is about 200 seconds. The disparity between those two different time scales, 200, a couple hundred seconds on the coronal side versus 40 hours, multiple days on the photospheric driving side, means you have this large separation of scales. And this photospheric driving is very, very slow process that evolves the corona in the atmosphere through a series of kind of quasi-static equilibria, right up until it's not in equilibrium anymore and you get an eruption. So that's what again, another reason why we're really trying to model this physical boundary. Why we're putting all of our emphasis on getting this lower boundary correct and deriving the simulation using that data. And just as a final sort of feature here, I want to show another one of these ab initio models. I need to switch my pointer to this. So this is another model simulation of how one of these active regions arises. 0 is our photospheric level, and this is showing density on this side of the data cube, temperature on this side of the data cube. So this is cold, this is very hot, this is, 1,000 Kelvin, this is 1,000,000 Kelvin, and the density drops off by 10 orders of magnitude between the convection zone below the photosphere and the corona above it. And this is a strong, buoyant tube of magnetic field, which is how we think an active region forms from popping up from underneath the surface. You can see it rise, poke through the surface, starting right here. And this is one of these synthetic magnetograms that James was talking about. So this is a slice from that photospheric layer showing positive magnetic field in white, negative magnetic field in black. And as it pokes through the surface, this is what we see. And so now again, you can imagine that this is what we observe at the surface. This is what's driving everything up in the atmosphere. And we really want to see, like James said, if we can recreate all the dynamics up above by just the observations in this well-observed boundary. So at this point, I'm going to actually leave behind the data and go just to the driving aspect. And I'm going to assume for the rest of this that we really have a time series of perfect boundary data. So we've measured the entire state variable, all the plasma and magnetic field variables, and we know what all the velocity are in a layer. And the question is, from that, can we recreate all the dynamics above that plane? A sort of second question is, okay, provided we can do the first one, how much of that data can we leave out and still get the answer mostly right, which is kind of our next step after we get this entire framework working. As Jane mentioned, there's been kind of a lot of work on this in solar physics in the past. Here's a non-exhaustive list, and there's substantial overlap. These are a bunch of different methods. I'm not going to go into the details on this, but the only thing I really want to point out and stress again is that none of these really use a fully open lower boundary that is consistent with the MHD equation that they solve in the rest of the simulation. So they either have, I would describe a lot of these as sort of a moving hard wall. They just sort of take a magnetic field that they observe, they shove it into the lower boundary, and they move it around in a way that isn't consistent, say, with the induction equation. What we want to do is relax that sort of method and try and do the lower boundary in a more self-consistent way. So our goal here is to write a boundary condition that approximates a given time series of observations, is fully open to the mass, magnetic flux, electric currents passing through it and evolving over time, makes limited assumptions about the external state of the system, because we don't really know what's happening down below that photosphere. We don't know what it looks like. So we want to use as few assumptions about that as possible. And we also want it to be consistent with our internal simulation equations. And for the moment, these are the equations that we're going to solve, the just ideal MHD equations. And the reason we're doing this is because if we can't do this for ideal MHD, then we can't do it. So we could add in two fluids, we could add in resistive effects, we could add in viscosity as needed in the future. But for the moment, we're going to focus on ideal MHD. Maybe we'll add in gravity there as an inhomogeneous term. And the method for reformulating the boundary condition is kind of the standard one of using the eigendecomposition of these hyperbolic equations. So we set this up as a system where we have our state variable of density, internal energy, the velocity field, the magnetic field, and we look at the time derivative of that variable, and the other equations are a matrix of coefficients that multiply the derivatives in each of the directions, and then maybe you have some inhomogeneous terms as well. So this is the start of what we're doing. It's a pretty standard way of solving these equations in the entire volume anyways, and we're going to formulate boundary conditions in this way. And the way to motivate our way through this is to look at what we know and what we don't know at the boundary. the time derivative of all our system of primitive variables, we can estimate that from observations. So we have a pretty good fix on what this is. In the boundary plane, all the transverse derivatives that are transverse to our boundary, we can calculate those directly from our ongoing simulation. The inhomogeneous terms are of course set by our model, whether there's gravity, resistivity, or whatever in that. And the thing that we actually need to set is that, and that we don't have a good fix on at the boundary, is what that normal derivative is. So in some sense, that kind of already suggests a solution where, typically to solve a system of equations like this, we're going to evolve the time system knowing all the spatial derivatives. But now we kind of have a fix on what one of those time derivatives is, but we don't really know what one of these spatial derivatives, so we're kind of exchange those two and try and solve for what the time derivative we need given the spatial derivative. But the tricky part here is that we're not completely free to choose what that spatial derivative is. And the reason for that is because MHD is a hyperbolic system. It has propagating solutions, and some of those propagate out of our boundary, and so are in some sense set by what's happening inside the simulation, whereas other of those characteristics propagate into our solution. And those are the ones that those are the only ones that we're really allowed to set using an open boundary condition. So again, focusing on the Z boundary, this is how we get to that description of those propagating solutions. I assume most people have seen something like this before, so I'm going to go kind of quick. We have these coefficient matrices. They look like this. They're just the coefficient matrices that multiply onto our derivatives in each direction. This is the AZ one in the direction normal to our boundary. AX and AY look similar. And if you do an eigen decomposition of this, you diagonalize this matrix right here, and you have a series of left and right eigenvectors that diagonalize the matrix. This matrix, diagonal matrix, are the eigenvalues of your system in that projected normal direction. And those are the velocities at which, or the speeds at which disturbances propagate in that direction. So in this case, you have a couple of eigenmodes that have velocities that are the bulk flow of your plasma. You have two more that describe alphanic disturbances, lowercase bz, which is the magnetic field divided by the root of the density in normalized units. And then you have two more that describe the slow velocities, the slow magnetosonic speeds, and two more that describe the fast magnetosonic speeds. So those are our propagating disturbances. Those are the speeds at which these disturbances propagate. And those are given by the eigenvalues. The eigenvectors tell us what those disturbances actually are. I'm not going to go into details here. There's a couple of Alfvén waves. There's the slow and the fast magnetosonic waves. And the real point is that these are all just coefficients that dot into the gradients of your your primitive variable. And so we can rewrite the MHD equations now just using those, we can group the terms in our MHD equations now using those derivatives. I've done that here. So we have the time derivative of our state variable. We have all of our transverse terms that I put into this T. We have maybe an homogeneous term in gravity. And we're grouping these characteristic disturbances now. That includes the diagonal matrix of eigenvalues, the left eigenmatrix of eigenvectors, and our derivative. What do each of these? This gives us a vector. What does each component of that vector look like? The first one of those just enforces the divergence of B. If I go, I don't want to go into this too much, but you can see there's this eigenvector just has a 1 down at the bottom. I guess this is our left eigenvector. There's a 1 down there that dots into the derivative of the magnetic field. When you set up MHD in this way, a lot of people remove this 1 because their numerical scheme automatically takes care of it. I include the enforcement of divergence of B just to be explicit. Other eigenvectors look like L2, which is basically an entropy disturbance that's infected at the plasma velocity. And the same goes for the rest of them. The alphanic disturbances have this sort of structure where primes are the derivative in that direction, and it propagates at some velocity that's basically Doppler shifted by the alphane speed in either direction, forward and reverse, and same with the slow speed and the fast speed. So if I rewrite MHD using these characteristic variables, I get something that looks like this. Say in the continuity equation, I now have basically broken up the dependence of how the density changes at a specific location based on the different types of nonlinear modes that propagate through it. And you can see here, I just highlight them. The entropy mode shows up in the density and internal energy. The slow and the fast modes show up basically everywhere. The alphane modes show up in the momentum equation and in the induction equation. And then of course there's transverse and inhomogeneous terms that modify all the equations. They come in pairs. So given the velocity at the boundary, one of these might be pointing into or out of the system. You might have a slow mode that propagates in or a slow mode that propagates out if there's zero velocity at that location. Or both of them could propagate in if you have a really strong inflow, or both of them could propagate out. Both the slow modes could propagate out if you have a very strong outflow. And same for all the other modes as well. So this then tells us how we're setting up our boundary condition. Now we want to divide up our system at the boundary in terms of one system that describes the outgoing modes, which I've labeled by the S and the LO, and one describing the incoming modes and the S and the LI. So we have our time derivative of our variables, our outgoing system, our incoming system, and then all the other transverse terms, which we can just calculate. So we're not going to deal with it. And that leads us to then how we specify our boundary. The number of incoming and outgoing disturbances changes based on what the velocity is. So if the velocity is less, again, we're at our lower boundary, so if our velocity is more negative than the fastest fast mode wave speed, then everything is going out and there's no incoming characteristics, and we have no way to really set that boundary condition. Or I should say, an open boundary condition is fully determined by the dynamics internal to the system for an outgoing shock. That's perfectly normal, it makes sense. And then as the velocity at that lower boundary switches between each of the eigenvalues of the system, between the fast mode and the alphane speed, between the alphane speed and the slow speed, between the slow speed and zero velocity, zero and slow speed, and on the way up for incoming plasma velocities, you get different number of incoming characteristics. It's important to point out that these are all on our boundary. These are all spatially and temporally dependent. So our vector of incoming characteristics that we have to set in order to define the boundary is a function of space and time. Again, this all so far is not terribly new. This was first written down for MHD, as far as I know, by Hedstrom in 1979, and you can see a lot of these. Most of these none of these were really done for data driving. They were all done for formulating other boundary conditions, everything from a hard wall to constant pressure to a constant mass flux through the lower boundary. What we're really trying to do is, using our knowledge of what this temporal derivative should be, figure out what characteristics we need to set in order to enforce that. That's the real name of the game for data driving on the sun. So sort of the current status, one other important thing. Even if you have one incoming characteristic, that might depend, say in the case of an inward propagating fast mode, that might depend on 7 of your primitive variable derivatives. And depending if you have more and more of these incoming wave modes, you might have an 8 for 8 comparison between the number of incoming disturbances and the number of variables that you need to set. And that makes it bit more of a tricky problem because there's not a one-to-one correspondence between how you set an incoming derivative and what boundary condition you're really enforcing. You could either have an under or over constrained problem. So you need some method to handle that under or over constraint system when you're defining what your boundary condition should be. And all I can really say on that right now is that we're working on that, but currently our code isn't stable. So I don't really want to talk too much more about that until I have something that's fully functional, which I hope to have pretty quick, because we have some ideas on how that's working. But I will say that for a much reduced and limited system, James has already demonstrated that you can do something like this and it does work. So this was his 2017 paper. This was looking at a 2D model of an emerging flux tube, and they took a slice of that boundary data and were able to exactly reproduce all of the dynamics that happened up above it using a much more simpler technique than what we're trying to do here with the characteristics. They could also interpolate that boundary. Instead of driving it at the Courant time of the original simulation, they could drive it at a much reduced series of extracted data. I think it was 12 minutes all the way down to a CFL time of about a second. Maybe I'm slightly wrong on that, but the order is right. So you can have a major reduction in sort of your temporal cadence. So you can do some smoothing and interpolation of that lower boundary and still get really good fidelity for your result in the simulation above. So the method has validity. Doing it with this characteristics isn't quite stable yet, but we're working on it. And now at the end here, I just want to go through a couple of other important topics and focus on how we're going to do validation, one of which is writing a very, very general non-reflecting boundary condition using a similar technique, and showing that at least shows us that the way that we've written the MHD equations in characteristic form and coupled that to our non-characteristic based simulation, we've used the simple finite difference version, and we've used a Lagrangian remap scheme, and we've coupled the characteristic formulation in MHD to both of those different numerical schemes and had it work for non-reflecting boundary condition. So we're pretty sure we're doing it right, and the problem of data driving is really in handling this under and over constrained problem. So for the rest of this, I'm going to focus on some work that my postdoc, Dylan Key, has been working on with non-reflecting boundary conditions. And a good test case for this is a Spheromac. I'm not really going to go into the details of it. If you want to build your own Spheromac, read this paper, use this potential, a vector potential for the magnetic field, take your derivatives and get B. But basically a Spheromac looks like this. If you're not familiar with it, it has an inner axis. I'll make sure that my pointer goes back to a laser pointer here. It has an inner axis that loops around in this direction. It has an outer axis where the field lines loop around in this direction. It's basically a big toroidal sort of thing that looks really cool and is fun to deal with. It's nice because it's a closed flux surface. So you can do all sorts of fun tests with it. Being a closed flux surface, you can take it and just advect it through your lower boundary and see how well you can push something through your lower boundary at any arbitrary speed you feel like and not get magnetic fields stuck in your system. So it's a good way to test those sorts of properties. You could also advect it into your system as a method of data driving if you wanted to do that. It's a more dynamic version of data driving. Depending on how you set up the background density and temperature, you can make this Spheromac puff up and expand. And when you do that and take a slice through one of the edges of it, say if I take a slice through this left edge of the Spheromac here and plot the magnetic field over here, you can see that it looks kind of like an emerging active region. It has some positive fields, some negative fields. So if I had plotted field lines here, they would connect one to the other. And this sort of pops out of the page as a very simple model for what an emerging active region kind of looks like. But for the rest of this, we're just going to focus mostly on a static case where we have a static magnetic field and we advect it and look and see how well we can do that process and model it passing through a boundary. Oops. And there's kind of multiple ways that you can set that up to make a boundary system that allows this to pass through and is non-reflecting. One is to take our decomposition of how the field of how the system evolves and set just all the incoming wave modes to 0, all the incoming characteristics, I should say, to 0. Another way is to say, okay, well, let's figure out what sort of the let's try and figure out what the amplitude of incoming waves is in the static case by multiplying by this matrix, the inverse of this matrix. And this is basically, when it multiplies our time derivative, this is basically our amplitude for incoming wave modes. We're going to set that to be, or the time derivative of that, and we're going to set that to be equal to 0, which implies that we should set our incoming characteristics to be minus that same coefficient matrix dotted into all the transverse terms. So this is basically, you set the wave modes, the incoming wave modes in such a way that it cancels out whatever dynamics would be driven by your derivatives in the transverse direction. This has been done before. There's a couple examples down here. Depending on what you're trying to model, either one of these is perfectly valid. And if you have a one-dimensional system or some sort of translational invariance, they reduce to each other. But it's kind of unclear which one you actually want to use in any given situation. And this shows an example of how we're doing it. This is our ground truth simulation. So this simulation, we started off with the static spheromac. We've embedded it in just a downflowing plasma. We have, and if I play it here, this isn't a real boundary right now. This is just showing where the boundary would be, but you can see it passes out the bottom. So this simulation on the left extends much further down below the bottom of the screen here. And that just gives us our ground truth that we can compare to our non-reflecting boundary condition. In this case, I'm showing the non-reflecting boundary condition, where I just simply set all the incoming characteristics to be 0, and we see how that does. Here in the gray plane is our actual boundary. You can see now nothing passes out the bottom because that's the bottom of our simulation, and it passes out great. It looks fantastic. So we're quite pleased with that. And I would point out that one of the nice things about this is we're not just passing a wave through the boundary or a shock through the boundary. We're taking an entire closed magnetic structure and advecting that whole thing through the boundary. It has its own currents, it has its own helicity, and we're advecting it out of the boundary. You could imagine putting one of these types of boundaries at the top of an eruption simulation and letting, say, a coronal mass ejection blast through your top boundary and still being able to continue running your data-driven simulation down below. So you can see those longer term dynamics after something is passed out of your boundary. That's the idea behind this. This is also a good test that we've really set up our characteristic system correctly and coupled that to our in this case, Lagrangian remap code, and that works. If I move on here, I just want to point out a couple of things. If I look at the ground truth simulation here and the non-reflecting boundary condition solution here, these are through a couple slices in time through this boundary plane, and I'm plotting the total magnetic field strength. You can see it looks pretty good for a lot of it, but there's some differences. And one of the things I want to point out is that the number of incoming characteristics is, like I said earlier, a function of space and time. So these colors here are basically different levels of, if I go all the way back, basically different levels of this pyramid showing different incoming wave modes. And you can see that self-consistently, the boundary condition handles that as a function of time. So out here, kind of outside of the spheromac in this region, we're in one level given by level 2, where the Alfvén speed, or where our advection velocity dz is greater than the outward propagating fast mode, but it's less than the Alfvén speed, which is 0 in this case, because there's no magnetic field out there. Whereas inside the simulation in these sort of light blue regions, the velocity is in between the slow magnetosonic mode and the Alfvén mode, again, in this outward-copying case. So in that case, there's three incoming characteristics in this region, and there's only 2 incoming characteristics in the surrounding region. And then at some locations, we get this dark blue where there's basically a very strong flow. And the way that the system has evolved, the outflowing velocity actually has a greater magnitude, negative magnitude, than the outgoing fast mode. So these are sort of basically a super fast shock, and we don't have any incoming characteristics in that case. Now we can compare this to the other simulation that I had, where we had canceled the transverse, or we cancel the, we just set the incoming derivatives equal to 0. This was for, sorry, I should say, this was for a very particular advection case where we set the original full embedded velocity to be less than the fast speed, but greater than the Alfvén speed in most of the sphere-Mach volume. If we set a very, very slow advection speed, so we're going to slowly move this system, this sphere-Mach, out of our boundary, and we try and do that with setting the incoming derivatives or incoming characteristics to 0, you get a very different answer, and you get a large departure from the ground truth simulation versus the non-reflecting boundary condition. And ultimately, the end state is the same. We fully advect the sphere-Mach out of our system, but we get a lot of field distortion during that process, basically because this isn't a very good representation, setting the incoming characteristics to 0. It's not a very good representation of the external universe. Basically, once the sphere-Mach starts passing out of the boundary, the magnetic tension and the magnetic pressure forces don't know anything about the external universe, so they start spreading apart. On the other hand, if we set the incoming characteristics to cancel out the contribution of those transverse terms, where those Lorentz forces are and pressure forces are pushing the sphere-Mach apart, then it stays together, it stays much more close to the ground truth simulation. And you can see the different number of characteristics that come in each case, very different. And that's because the velocity, the vertical velocity at this boundary is strongly constrained by canceling out these transverse derivatives in this case, where it isn't as constrained in this case. So which one of these is really better? It really depends a lot on the simulation, on the situation. This shows 2 cases where I've done something, or rather I should say Dylan has done something quite crazy, where we've taken the sphere-Mach, embedded it partway through our boundary, and just kept the whole thing stationary. So there's no initial flows here. So 2/3 of this sphere-Mach is inside the simulation. 1/3 of the sphere-Mach is outside of the simulation. There's no initial velocities. I'm showing you a top-down view. And you can see here the starting state in both of these simulations is the same. If I can pause it. This is a top-down view showing the field lines and the magnetic field in that lower boundary. And if I jump to the end, you get very different dynamics based on these. Which one of these is correct? Well, this looks more like what we would expect a static sphere-Mach to do, but that may depend on the situation. It depends on how you model that external universe and what you want it to be, and what you think is a correct model for the outside. In this case, canceling the transverse terms is probably correct, and setting the incoming ones equal to 0 is probably incorrect, but that might be different in some other situation, say on the sun. So this is my last slide, and sort of my take-home messages that I want you to leave with is that models of the solar atmosphere contain a very well-observed natural boundary that drive the solution of the system above it. And the way to model that is with a fully consistent open boundary condition at your lower boundary, and maybe to do the data driving. And maybe you want a non-reflecting boundary condition at your top boundary as well, because you need to, and you're going to have to do something on the sides, obviously, too. We'll leave that for later. Generally, the non-reflecting boundary conditions work, and by work, I mean they don't crash. They allow things to pass through the boundary, but a lot of times it's unclear exactly how setting those, what you're actually implying about the surrounding universe that you are effectively modeling, but you haven't really thought maybe about exactly what that model should be. And I haven't shown here a lot of the other tests that we've done that are less strenuous than the Spheromac tests, where you just let waves pop out, shocks, rarefactions. All of those work just fine. They exit the boundaries. Various magnetosonic alphane waves go out just fine. But depending on the advection speed that you use for some of these more stringent tests, where you're advecting a Spheromac out, sometimes the incoming characteristics, setting those to 0 seems to work better. I haven't shown it, but sometimes setting them to cancel out the transverse term seems to work better. And it's unclear exactly which one to choose in any particular case. Ways to resolve that might be adding in more global constraints, which we are kind of pushing or moving towards in solar physics. Maybe you want to constrain how much helicity, magnetic helicity, is moving through your boundary, or what the total energy flux is. Another way to maybe add a further constraint that gives you some information about what's going on in the external universe. So I'll leave it just with, there's a couple of papers that we're working on. They're in prep. One by myself, one by my postdoc, Dylan Key, who's done all of this nice non-reflecting boundary condition work. And look for those later this year. And I'll leave it at that. Sorry, I'm a little bit over.
All right, awesome. Thank you very much, both James and Lucas. That was very interesting, quite a lot of information. Does anyone have any questions for either of the speakers? I think I'm going to go back and watch this a second time just to make sure I fully understand everything, but it's really cool.
Yeah, sorry, that was a shotgun of information, I know.
Hey, Lucas and James, thanks so much for that talk. This is exactly the kind of talk I was hoping to see when we put this group together. You know, we're from the geospace side, we talk to geospace people, but there's clearly lots of cool stuff going on in other disciplines. And, you know, as you know, we record this talk for a reason, because actually we get quite a few views on YouTube. We had 90 views in the last talk, for example. So I will make sure this gets sent around to the geospace ITM community, because I think there's a lot of cool stuff here that maybe they may not have thought of, or they might trigger something different. So I really appreciate you're doing this. And I think, again, you're kind of the first one out the gate here to do something totally different than what my community has seen. So I really appreciate that. Thank you.
Thank you.
Yeah, no problem. Yeah, I mean, our situation is very different from what I imagine data assimilation is. I used to work in oceanography, where, you know, you've got dense data in the middle of your volume. So, and the boundary conditions are kind of an afterthought. For us, the lower boundary condition is everything. So I think anything we can learn beyond what we've done from the community is really valuable too.
Yeah, it's kind of similar in a way. On the geospace side, we have the upper boundary condition, the solar wind coming in. And then we have another boundary condition, which is the ionosphere. And the ionospheric boundary can be kind of difficult. You know, people treat it differently. And then in the middle, we don't have much to constrain it at all, because we don't have any measurements out there. So you're kind of constraining your system by these two boundary conditions and how you alter it. Yep.
Just to relate to a third field really quickly, though, is in ionospheric modeling. A lot of exoplanets are out of reach because they're in their subalphanic region, because you can't really properly handle that solar wind boundary condition as if it was super alphanic. So I haven't thought about it very much. Maybe this would be an interesting technique to try and employ there as well.
So in the solar wind anyways, this type of method has been done, but usually make very strong assumptions about what that inner boundary system is. Basically, you have a super alphanic inflow, right? Which strongly constrains which level of that sort of incoming characteristic pyramid that you're in. Mm-hmm. Once you move down to the photosphere, like you say, or maybe some other places in the heliospheric system, man, all bets are off. That velocity can come in or out, the magnetic field can change, the pressure and the density can change. And that's what makes this such a difficult problem.
Right, sure. Awesome. Any final questions? All right, well, thank you very much again, James and Lucas.
All right, thanks so much for letting me present this. This was fun to put together.
Yeah, absolutely.
Yeah, thanks.
Have a great day, everyone.